Hello and welcome back to my channel. Today we will be talking about the Wideband Frequency Modulation or WBFM, a core technique behind the high quality wireless communication systems like FM radio, television, sound and modern transmitters. In this lecture we will explore how WBFM signals are generated using both direct and indirect methods, the role of components like Varactor Diodes, Reactance Modulators in direct FM synthesis, and finally a comparison table to help you choose the best method for your design, whether it is for learning, simulation or real world application. So in this lecture basically we will see a brief introduction to those methods, and in the later lectures we will discuss how each method works and they either generate or detect the wideband frequency modulated signal. Before we dive into these techniques work, let's take a quick look at the different methods used to generate and detect the wideband frequency modulation signals. Each method offers a unique balance of complexity, performance and cost. Understanding the options will make us better design choices later on. Let's start with the simple breakdown. Wideband frequency modulated signals generation methods are of two types: indirect method and direct methods. Indirect method include Armstrong method, and direct methods includes LC oscillator method, Varactor Diode method, Reactance Modulator method, and PLL-based FM generation. Now that we have seen the big picture, let's take a closer look at how wideband frequency modulated signals are generated. There are two main approaches: the indirect method, which builds up the wideband frequency modulated signal step by step using stable low frequency components, and the direct method, which creates the frequency modulated signal directly by varying the oscillator's frequency in real time with the message signal. Each method has its own strengths depending on the application. So let's start with the indirect method, which is also known as the Armstrong method. The Armstrong method is an indirect way to generate the wideband frequency modulated signal. It begins with a stable crystal oscillator to produce a carrier, which is then phase modulated to create a narrowband frequency modulated signal. The signal is then passed through frequency multipliers to increase both modulation index and carrier frequency. Finally, a mixer and a bandpass filter shift the signal to the desired RF band and clean up the output. This method is essentially popular in FM broadcasting, where high signal stability and quality are essential. So here are some pros and cons for this generation method. Pros are: it offers excellent frequency stability due to crystal oscillator reference. It is ideal for high quality precise wideband frequency modulation. Delivers a consistent low drift performance over long operating times. Cons are: it is complex and bulky, involving multiple stages. Higher cost compared to direct generation methods. Not suitable for small scale or low power transmitters. Now let us take a look at the direct methods for wideband frequency modulated signal generation. Unlike Armstrong method, direct generation techniques apply the message signal directly to the oscillator circuit. These methods shift the oscillator's frequency in real time, offering simpler hardware setups, especially useful for low to medium complexity application. First method is the LC oscillator method. In this approach, message signal modifies the tank circuit of an LC oscillator either by altering its inductance or capacitance. As the signal voltage changes, the oscillator frequency swings accordingly, producing frequency modulation on the fly. It's often used in educational and experimental setups because of its simplicity. Some pros are: very simple circuit, great for beginners and demonstration. Low cost hardware, no specialized components are needed. Quick to build for proof to concept lab setups. And cons are: poor frequency stability due to the component drift and temperature effects, and high sensitive to interference and variations, not suitable for high performance or precision systems. Next is the Varactor Diode method. The Varactor Diode method uses a diode as a voltage control capacitor in the oscillator's tank circuit. As the reverse bias voltage across the varactor changes due to the message signal, its capacitance shifts, causing the oscillator's frequency to vary. This technique is widely used in compact RF and IC based designs. So this method is compact and lightweight, ideal for integrated circuits or IC application, allows precise frequency tuning using small voltage changes, easier to implement in modern PCB layouts and digital system. Some cons are: requires automatic frequency control or AFC to maintain long-term stability, narrower tuning range compared to other methods. It shows nonlinear behavior at the extremes of tuning range. Next is the reactance method. This method uses a transistor circuit like BJT or FET to simulate a variable reactance. When inserted into an LC oscillator, the message signal controls the transistor's characteristics, which in turn modulates the oscillator's frequency. It's a small blend of linearity and simplicity, making it practical for mid-level FM transmitters. Some pros are it offers more linear response compared to Varactor-based circuits, good tuning flexibility and suitable for analog modulation, reliable choice for medium power FM transmitters. Some cons are low input resistance at high frequencies can affect oscillator operation, requires precise component selection and biasing for proper performance, moderate design complexity, not as plug and play as simpler methods. Now, next is the PLL-based FM generator. In this method, a phase lock loop or PLL is used to generate FM signal by controlling a voltage controlled oscillator or VCO. The message signal is applied to the input of the PLL, which adjusts VCO frequency in response to the signal's variation. This setup delivers a precise, stable frequency modulated output, and it is widely used in the digital communication system and hardware defined radios. Some pros are highly stable and accurate even over long operating periods, digitally tunable, making it ideal for modern programmable systems, easily integrates with software-defined radio or SDR platforms. Cons are requires complex control circuitry or specialized IC, higher power consumption compared to basic analog methods, slightly slower response in high-speed application if not properly tuned. Now that we have explored the methods of generating FM signals, let's compare them side by side. This will help you decide which method fits your application, whether for learning, prototyping, or professional use. Let's begin with the generation techniques. First method is the Armstrong or indirect method. It has a very good stability. It has a very high cost, very high complexity, and it is used for FM broadcasting. Next is the LC oscillator generation methods, which has a very low stability, and it also has very low cost and complexity. It is used for educational and basic systems. Next we have the Varactor system. Here the stability is higher than LC oscillator but lower than Armstrong method. Cost and complexity are also in the medium level, and it is used for IC based analog designs. Next we have the Reactance Modulator, which has higher stability than LC oscillator and Varactor Diode. Cost level is also medium, and it is used for mid-range FM transmitters. Finally, we have PLL generator, which has the greater stability than LC oscillator, Varactor Diode, and Reactance Modulator. The cost and the complexity is medium. It is best used for SDR and digital FM systems. As you can see, the Armstrong method stands out for its precision but comes with high cost and complexity. On the other hand, direct methods like Varactor and Reactance Modulator offer a good balance for compact and mid-tier application, while PLL generators are a top choice for modern digital designs.